Hi everyone, so it's Wendy again, and today I will be going over modes of ATP generation. There are two ways that microbes can actually generate ATP, and one of them would be substrate level phosphorylation. Another one is via transmembrane ion gradients. Before I go over what substrate level phosphorylation is, it's important to know what oxidation and dehydrogenation both are. These are both important within the actual generation of these ATP molecules. So with regards to oxidation, this will just be a recap. So with oxidation here, we have an acceptor. An electron is being extracted by itself and then passed on to an electron acceptor. So basically, oxidation, an electron is being transferred over to an acceptor. With dehydrogenation, you do see also an electron being transferred as well as with a proton. So there is an electron and a proton both being transferred, but this time it will be accepted by an H-accepting molecule. So it has to be specifically an H-accepting molecule. Because if you notice in the name, dehydrogenation, so you're actually taking away a hydrogen. So you're taking away a hydrogen here and you're actually replacing it and giving it to a hydrogen acceptor. When you give a hydrogen to a hydrogen acceptor, it becomes now a reducing molecule. So when it's a reducing molecule, it has reducing power. Basically what reducing power is, it is a source of electrons that make more reduced building blocks from precursor metabolites. It will make more sense as I actually go over substrate level phosphorylation. But an example of what building blocks are and precursor metabolites and how they relate is amino acids. So amino acids are building blocks, are the building blocks of proteins. So that's an example of how building blocks and precursor metabolites are related to this topic. So now that we know what oxidation and dehydrogenation both are, we can go on and start explaining what substrate level phosphorylation is. So again, oxidation, you're giving an electron to an electron acceptor. Dehydrogenation, you're taking an electron and a hydrogen, so which is a proton, electron and a proton to a hydrogen acceptor, which will then give it reducing power. So that is a recap of oxidation and dehydrogenation. So now that we know what oxidation and dehydrogenation are, we can go on and explain substrate level phosphorylation. So as I mentioned earlier, I did show that we had that molecule that can accept protons. So in the midst of this substrate here being phosphorylated, that is actually occurring due to the proton being transferred to a proton acceptor. So that energy is what allows this product to be phosphorylated. When this product is then phosphorylated, we can then transfer that phosphate to an ADP molecule. It becomes adenosine triphosphate. So this would be diphosphate because it has two phosphates. It then becomes a triphosphate when the phosphate is actually transferred over to that adenosine. So it becomes a triphosphate. So 3 phosphates on that molecule. So again, with substrate level phosphorylation, it is an inorganic compound that is phosphorylated. The only way that this can happen is if there is a proton being transferred to a proton acceptor. So you have to remember that there's simultaneous things happening. Things will be happening all at the same time in a cell. So you have to have a proton being transferred so that this product can become phosphorylated And from there, this phosphate is what will be transferred to this diphosphate to become a triphosphate. And that's literally what substrate level phosphorylation means. It is happening at the level of a substrate, of the substrate. That's why it's named that way. So it's substrate level, and then you have phosphorylation. So at the level of the substrate, you are having a phosphorylation happening. So literally this phosphate is being transferred to here, then being transferred onto here to become this triphosphate. So that's the recap for substrate level phosphorylation. Many microbes also use another form of ATP generation, and this one is actually called transmembrane ion gradient. So this looks complicated right off the bat, but if you digest it piece by piece, it shouldn't be so bad. Overall, the concept, a way to create the actual gradient itself is by removing electrons and protons from the proton acceptor that I mentioned earlier. So it would be NADP or NADH. So it would have that H attached to it at the membrane. So yes, that would be here. So the acceptor is the NAD or NADP, and the acceptor, it is red, but that would be once it has that proton attached. So that basis is pretty important with ATP generation when it comes to proton acceptors. So it's important to note that those are necessary to create this gradient, as well as earlier when I mentioned substrate level phosphorylation. Those are pretty much the most essential molecules for any energy to be created. So within the transmembrane ion gradient, there are two types of gradients. You have first the electron transport chain, and then you also do have the proton motive force. So first, I will explain the electron transport chain. So for the electron transport chain, you have a number of membrane-bound electron carriers. So those carriers are what drive the gradient. They will be transferring electrons to each other on the membrane between donor and acceptor based on their redox potentials. So that would be another video later on that I'll go over redox potentials and just how that relates to oxygen and respiration. But for now, you would just note that electrons are being passed down the gradient from carrier to carrier. This step right here is important for both gradients. So you have the proton acceptor already having that proton on it. So when it releases that proton into the gradient, it is also releasing an electron. And that electron is the one that is being passed down that gradient from carrier to carrier. So this, as I mentioned earlier, is a very important step in cell energy generation. So again, we do see this proton that is removed from the proton acceptor. It is actually pumped outside. It's actually pumped outside the cell membrane. And as that is occurring, you also do have an electron that is ejected and passed on from electron carrier to electron carrier. And that itself is what creates the electron transport chain. So that's an electron being transported down a chain, if you really put it into perspective. Now that we know that what the electron transport chain is, we can now talk about the proton motive force, and that itself has its own drive. So the ATP synthase is what drives the proton motive force, which is also a proton gradient. The structure of ATP synthase itself has a couple components to them. So F0 is the very top part, and that itself is an open cavity. It then has a lower portion, which is this right here. That itself is called the axle. So once protons are inserted here, this axle will rotate. So once the protons move down the gradient into this open cavity, the bottom part of this open cavity will start rotating due to that spontaneous movement of that proton down the gradient. Once this starts rotating, that also causes another reaction. Therefore, that allows for F1 to catalyze the phosphorylation of ATP, again, diphosphate, becoming an ATP. So again, let me recap what just happened. So the open cavity allows for the proton to go down the gradient, which then rotates the axle, and that in turn activates F1, which then allows for a phosphate to bind to ADP and therefore create ATP. So it can be then said that through the flow of protons, that is what catalyzes the phosphorylation of ATP. An influx of protons causes ATP. These protons are located outside the cell membrane. Another interesting fact about this structure is that ATP synthase can actually work in the opposite direction. So right now I explained that the protons can go inward, but it can also do the opposite, so go outward. The flow of protons going in or out of the cell is dependent on the concentration of the reactants and products. What that means is that if there is low ATP inside the cell, you have a low amount of ATPs in here, and you have a lot of H pluses in here, that will literally cause for the protons to come in, therefore cause the axle to rotate, then catalyze the formation of more ATPs. So it'll cause an equilibrium. On the other hand, if you have too many ATPs here and very little protons up here, you will actually see the export of protons. So just to also create that equilibrium. So that was pretty much a recap of what substrate level phosphorylation and transmembrane ion gradients are. And again, those are both forms of ATP formation in microbes. So that was the recap of how microbes create ATP. Thank you for watching my video. Hope you like and subscribe. If you have any questions or comments, please leave me a comment below. Thank you.